Welcome back. We're now continuing on with this worksheet for C2 energy. I'm going to do a few more selected ones now. I'll do question 5 and then a couple on the other side. If there are any other problems, please email me. Question 5, when we have a look at it, is about a bullet of mass 8 grams. That's the first thing we should notice, is that's in grams, not in kilograms. And it's traveling through the air with a velocity of 500 meters per second towards a target. So it's going to go through this path here. And it drops through a vertical height of 125 meters there. Let's go through each of the questions sequentially. So the first one was, what's the change in gravitational potential energy? Now, even though the path is here going through a diagonal, or actually it's parabolic, path there, it's only gravitational potential energy is concerned with the vertical displacement. So in this case, delta H is 125. So let's get here. So 5A, we know that delta H is 125 meters. We don't care about the length of that path. It's just this section just here that we are needing. So delta U would equal mg delta H. Now the mass of this object is 8 grams, okay, which is 0. Now if that was 8, that's 800 milligram, 800 grams. That would be 80 grams, and that would be 8 grams. Okay, so that's the way I'm working it. So in kilograms. So that's 0.008 times 9.8 times 125. Type it into a calculator now. We get, let's see, 0.0, oops, not turning on. There we go. 0.008 times 9.8 times 125, and that gives us 9.8 joules. Okay. B, we have to calculate the bullet's kinetic energy when it leaves the gun. So the kinetic energy would be a half mv squared. So it's a half times the mass, which is 0.008, times the velocity. Now it's massive velocity, obviously being a gun, and so it's 500 meters per second squared there. Meters per second all squared, not per second squared, that's acceleration. So that's 0.5 times 0.008 times 500 squared, and that's 1,000 joules. Okay, so it's got 1,000 joules when it leaves the gun, and it gains another 9.8 joules as it drops. And question C says, how many joules does it have when it hits the target over here? Well, it would have this amount of energy from the gun, and it's got an extra 9.8. So the total energy, E total, would equal 1,000 plus 9.8, which is 1,009. 1,009.8 joules. Okay, at the other end. Looking at question 6, 6 is just simply trying to work out gravitational potential energies when I'm telling you move it from the shelf, from the table, and so on. So if you're confused with that one, draw a little diagram as to where it starts and where it ends as well. There's question 7 is checking whether or not you remember that work done is the change of kinetic energy. This one here, question 8, a mass is sliding down an incline from rest. The change of kinetic energy is simply always the final velocity squared minus the initial velocity squared. So it's using this formula over here. So please realize that it's v squared minus u squared. Please don't make it v minus u all squared. Okay, so it is v squared minus u squared. The squared cannot be on the outside of that bracket. Okay. Question 9, we'll do question 9 now. Pop over, just reading it. Question 9 says, a 5 kilogram mass is dropped from rest 12 meters above the ground. What's the kinetic energy as it strikes the floor? and what velocity does it strike the floor. So I'll just get a little bit more room here. Good. So it's question 9. So a little diagram where up here where our velocity equals 0 and it's 12 meters and the object is dropped onto the floor. Here's the floor down here. And the object is 5 kilograms as the mass moves down. Okay. Rightio. The first thing is, what is the kinetic energy as it strikes the floor? Well, at the top up here, the kinetic energy equals 0 because it is stationary. If my velocity equals 0, I have no kinetic energy. So as it goes down here, it's going to gain kinetic energy. And where's that kinetic energy going to come from? That must come from the change in U. So at the change in U would be mg delta H, and the mass is 5 times 9.8, and its initial velocity, delta H would equal H final minus H initial, which is the floor, which we'll call 0, and this would be 12 meters. So it's 0 minus 12. And putting that into our calculator, we get 5 times 9.8 times negative 12. And that's negative 588 joules. What does the negative imply here? That we're losing gravitational potential energy. If we're losing gravitational potential energy, what is it being converted into? This must be converted into kinetic. So at the bottom, we must have gained 500. Just tidy that up so you can see what I'm doing. At the bottom here, we must have gained 588 joules of energy. Okay. If that's what we've got, which it is, we can now calculate the velocity it strikes the ground, because we know that the kinetic energy is a half mv squared. It's a v. So 588 would equal 0.5 times 5 kilograms times v squared. We just rearrange that to find v. Okay. Question 10 often causes a problem because it's got a energy capacity in it. So let's move on to question 10. Question 10 is how much work is done by the engines of a rocket, and the rocket is 650 kilograms in mass, as it accelerates from this velocity to that velocity, from 7,000 to 9,200, okay? And that's going to be quite easily worked out. That's going to be using the formula, the change in kinetic energy is a half mv squared minus u squared. The second part of the question always causes problems because it's about energy capacity of hydrogen here. So let's work it through. So we need question 10 to be done first. So let's just quickly do question 10a. So 10a has us accelerating from our initial velocity is 7,000 meters per second to a final velocity of 9,200 meters per second. Okay, so the change in kinetic energy, delta K, is equal to half mv squared minus u squared. And the mass of this rocket is 650 kilograms, and it's v, which is 9,200 squared minus 7,000 squared. And popping that in, 9,200 squared minus 7,000 squared. So it's 1.1583 by 10 to the 10 joules is needed. Let me just check that I've got the right answer. Otherwise, it's no use keeping going. Yep, that's good. Okay. Right, so that's the amount of energy that is needed to do this change of velocity. Okay. So if we don't, where's that energy going to come from? It's going to come from the hydrogen. We're burning hydrogen, so it says the second pass of the craft burns hydrogen fuel, and it has an energy capacity of 142 megajoules for every kilogram. So if I burn 1 kilogram of hydrogen, I get 142 million joules. So how many kilograms would I need to get that this amount of energy? So 1 kilogram gives us 142 million joules of energy. Okay, so how many of those fit in that? So that will give us the amount of kilograms that we need. We need this much energy here. Okay, so if I was to take this and divide it by that, that will tell me the number of kilograms that I need. So that divided by 142 by 10 to the 6 equals 81.57. So that's 81.57, or in other words, 81.6 kilograms is needed for this burn of to create this velocity change. Okay. Question 11, which is the last one I want to do because it contains friction. Question 11 is asking about how much friction on a box. So I want to do this because it's quite important when it comes to work. A 20 kilogram box is traveling at 8 meters per second and it slides to rest. Why is it sliding to rest? It's because it's got a frictional force on it and that opposing its motion. And it does this in a distance of 16 meters. So we want to calculate the kinetic energy change. So the first thing it asks to do is, for 11A, is to find delta K, which is a half mv squared minus u squared. Okay, so it's a half. The mass of this box is 20 kilograms. The final velocity is 0, and the initial velocity is 8 squared. Okay, using the calculator, I'm just going to make the 8 squared. I know it's going to be a negative at the end. It's negative 640 joules. In other words, we're going to lose 640 joules as the object slides. So it had 640 joules here, and as it slides through its 16 meters, it will come down to 0 joules here. Okay, so where has this energy gone? Okay, the energy has been released in some form, and in this case, it will be converted into heat or sound or other forms of energy. So what is the force that does this? It's friction, and friction is acting against it in this direction. Okay, so can we calculate the frictional force against the motion? Well, yes, because we know that delta K is equal to the work, and therefore delta K must equal force times displacement. Now, the force is acting in the negative direction, so this would be, we're going to use the positive version of this because we're just going to equate this to that force. So we know that that F and that S is going to be the opposite direction. I will say that again because I've confused you, I know that. The force is acting this direction, so my displacement has to be in this direction. So what is the displacement in this direction? It would be negative 16 meters. Remember, when we use this formula, when we use this formula, the force and the displacement must be in the same direction. So if the frictional force is acting this way, then displacement must be this way, but we're moving this way. So if that's the direction of motion, then displacement this direction will be negative 16. So this will take care of these two negatives. So we get minus 640 would equal the force, in this case the force is friction, times the displacement, which is negative 16. Okay. And that means that friction is equal to 640 on 16. And that equals 40 newtons. Now, when we did do this, most students would simply ignore the negative over here and just calculate it using the positive values, and you get the same answer out. I just wanted to make sure that you're welcome to do that. I just wanted you to to understand why and how these two negatives in reality do cancel. Okay. If you could just work your way through to the end of the worksheet now. I hope you're having success with it. If there's any problems, please let me know. Thank you.